I'm going to talk about a system which is a bit different from what you've heard about so far, and that will be strongly interacting fermions. So far, this is the main topic of the workshop, but we'll have these fermions also interact strongly with light. And that's the thing which we've been developing over the last years now at EPFL, and I'm going to show you how we can use this light-matter interaction in order to introduce long-range interactions and strong long-range interactions between fermions, and that turns the system into this charge density wave state. So we achieve that by taking a unitary Fermi gas, as you know now, for the last few days at least, and placing it in between two mirrors forming a high-finesse cavity. So before doing that, let me first introduce the people who've actually done this work. And so I'm going to say things like, we do this, we do that, but it's understood that these are the people actually doing it. And in particular, Tabea, who is in this room, who has been really pushing this project very strongly. So I also would like to emphasize theory collaborations. This will come in the explanations, but this is clearly something where without the theory input, we wouldn't go very far. And in particular, for what I'm going to present, the main collaborators would be the groups of Thierry Giamarchi and Eugene Demler. So let me start and set the stage. So we'll be interested mostly, and essentially almost exclusively, in atoms in free space. So there won't be any optical lattice. And I'd like to start by just reviewing a little bit the kind of things that can happen if you have a Fermi gas in free space and you start to put in interactions. And things which everybody knows is that if you have a little bit of attractive interaction on top of the spherical Fermi surface, then the smallest attractive interaction will make the Fermi surface unstable against Cooper pairing. So if you have sufficiently low temperature, attractive interaction will always lead you to superfluidity and pairing. And that's something which we know very well in our community. There has been now, I think, about 20 years of investigations of systems with strong attractive interactions, and we've heard about the state of the art in this respect over the last couple of days with the talks of Henning and Martin. So this is a system which we know very well, even though we keep learning new things and new details. There are a little bit of points which are still not completely known. But this, as far as my talk is concerned, will be considered something that's well understood. Now, if you go to repulsive interaction, on the other hand, then essentially the system is going to be very robust, again, moderate repulsive interactions, and you really have to crank up repulsion very, very large until the system starts to again get unstable against forming essentially magnetic domains if you conserve the total magnetization. This is the Stoner instability that can happen in free space, and that requires interactions that can really compete directly with the Fermi energy. It's a topic which also has a very interesting and long story in our community. It started with work by Wolfgang Ketterle a bit more than 10 years ago. First, seeing indications that strong repulsion was actually destabilizing the system. And then sort of it was clear that there was other competing instabilities, and I would say the most recent investigations that have been performed in Florence in the group of Giacomo Roati seems to indicate that even though the system clearly shows some tendencies at sort of showing anti-correlations between spin up and spin down for strong repulsion, the competition with three-body recombinations is making the system essentially unstable, and it's, I would say, not completely clear whether it's actually possible to stabilize the ferromagnetic, the Stoner ferromagnetism in free space for fermions. So this this was for attractive and repulsive interaction, and if there would be only contact interactions, that would be essentially the end of the story, right? You can have either strong attraction or strong repulsion, but it turns out that if you have now interactions with finite range, in particular long-range interactions, a lot of other things can happen. And these other things will be typically like crystallization or the formation of patterns and self-organizations of different kinds. And this is now a much richer pattern of sort of landscapes. You have all kinds of charge density waves, Wigner crystallization, and so on. And depending on how these interactions actually look like, this kind of things is suddenly very rich. And for that, you don't even need an underlying optical lattice, right? Just the structure that there is in the space dependence of the interaction will actually do the job of forming these structures. And that's the main thing which we'll be interested in. That's something which is growing in our field. But for fermions, there's actually not so many experiments. I think the first one I could find back is that experiments by Wasim Bakar with Rydberg dressing of fermions in an optical lattice, where there was indications of density wave, at least stabilization of some density wave patterns. There's now a new generation of polar molecules experiments, which in principle have strong finite range interactions. This is now taking place. As far as I know, there's no indications yet in these systems of things like Wigner crystallization, but I mean, this is evolving very fast. So this is clearly something which is, we're going to hear more certainly in the next years. And then there are cavity-induced interaction, which is the topic of my presentation, which is happening now since 2021. The group of Heibing Wu in Shanghai demonstrated first strong cavity-mediated interaction on free fermions, and this is something we've also been working on since then, pretty much. So I will explain how this works now. So if you have atoms that are placed inside the cavity, then these atoms can actually interact over long distances by exchanging cavity photons with each other. So the model would look like this. So there's just the light-matter interaction part. There's, of course, an underlying Hamiltonian for the atoms themselves, which I don't write. And light-matter interaction in the regime where the light is far detuned from atomic resonances is just dispersive, and it looks like that. This is just the dipole force exerted by the total electric field intensity onto the density of atoms, right? So there is, of course, a detuning. That's the energy of the cavity photons. And then the total electric field inside the cavity is generated either by the cavity photons themselves or by a side pump, which we can send onto the atoms sort of from the side of the cavity. And that's sort of this classical pump beam that we can add. And now when you send this pump beam, what can happen is that atoms in the cavity can Rayleigh scatter the photons. Now, and here comes the point where you actually need a cavity, which is that the Rayleigh scattering, if you are in the high finesse cavity, is going to happen predominantly in the cavity mode as opposed to free space. If there was only free space scattering, there would just be spontaneous emission like you have with any kind of far-off resonant beam. But if you have the cavity around, the rate of scattering inside the cavity per atom is going to be enhanced by an amount which is given by the cooperativity. Cooperativity is proportional to the finesse of the cavity. So if you have a very good cavity, then essentially the scattering process takes place in this mode, and you can forget about everything else. Now, as a result, once a photon is inside the cavity, then every other atom that happens to be there as well sees the photons and feels the dipole force exerted by this photon. And now what we can do is, we go back to this formula here, there is a certain detuning here, which we can control, and that tells us how off-resonant that particular scattering process is. If we make this off-resonant, then the next resonant terms comes at next order, and it will look like that. So this is essentially an interaction potential. So you see here density times density. The strength of this interaction potential is controlled by these terms here. One of them is the dispersive shift per atom. So that's the cavity, the light matter coupling between photons and atoms. One of them here is just the dipole force exerted by the pump beam. Right? So that's the strength of the beam that I send from the side. That's something we control experimentally. And there's this 1 over delta, because this is the energy denominator, that can be positive or negative, and that's something we choose experimentally as well. So now the important thing is what's the shape of this potential, and it's given by these functions here, which are the mode functions of the electric field that the system is exposed to. So there is a pump field and a cavity field, and these essentially are sines and cosines, simply because we have Fabry-Perot cavities and essentially plane waves or standing waves that we use to illuminate the system. So this is a very weird kind of interaction in which the potential is essentially a cosine and a sine, and these particular wave vectors that are picked up by the system. This is determined by the directions of light and the direction of the cavity axis. This is something we choose to begin with, and that's something which is determined once and for all. And you see this interaction is sort of local in momentum. So it's completely extended in space, that essentially that amplitude does not decay with distance. So no matter how far away the atoms are, they essentially exchange photons as long as they are in the cavity mode, which for us means that it's essentially at infinity. And you have this underlying structure. That's something which actually has been discovered, to my knowledge, by Gerhard Rempe in 2000. But this is something which is now being exploited in a very wide variety of experiments. There are many groups now working with this kind of cavity systems, and you can use this for all kinds of purposes. You can place Mott insulators and see the competition of this interaction with contact interaction. One can use the dissipation channel that's provided by the cavity, because photons go out in order to create phases of matter like dissipative time crystals, adiabatic pumps, and so on. One can use the mode structure of the cavity to engineer interactions in ways that are not exactly what I described. And then one can also use this interaction in a flavor in which it introduces spin exchange rather than just optical forces. And with that, you can actually create all kinds of long-range spin models for quantum simulation purposes, but also for precision measurement. If you want to know more, there's an exhaustive review of this field that's from 2021. Okay, so this is what we're actually using. So that's a bit of a technical slide. This is the system as it looks like in a simplified sketch. We have this cavity inside the vacuum chamber. The mirrors are separated by 4 centimeters. This is really a macroscopic object. And in between these 2 mirrors, we do all our experiments. And these are the numbers. Again, that's mostly for the experts. And the main thing is that we are doing all the evaporative cooling, laser cooling, and so on in between the 2 mirrors. And then there, we actually produce unitary Fermi gases with a few hundreds of thousand lithium-6 atoms down to temperatures of the order of 0.1 TF, which is probably the lowest temperature we can anyway measure. And again, that's a technical point, but even if you don't care about cavity QED or quantum optics, cavities are actually very good because it makes a super clean dipole trap. And now we've learned how to use the simple Fabry-Perot cavity for the entire evaporative cooling process, from capturing of the laser-cooled atoms all the way down to quantum degeneracy. And that means we have a very nice, very clean Gaussian dipole trap. It's probably the only Gaussian dipole trap I've ever seen in my life. Actually, we do that with less than 1 watt total laser power for the dipole trap. That's actually something really nice. So that actually, even if you're not a quantum optics person, cavities are actually already very good. So, okay, that's the basic system we have. And now, on top of that, we're going to have the 2 kinds of interaction. One of them is the contact interaction I mentioned at the beginning. We are working close to the Feshbach resonance. That's a regime in which the system forms Cooper pairs and is superfluid all the way in the BEC-BCS crossover. I don't elaborate more on that. And then we have the long-range interaction mediated by the photon. So this is one way to represent it. So technically, we have the atoms inside the cavity. We illuminate from the side with a pump beam that has a small angle with respect to the cavity axis of 18 degrees. And then we have this momentum recoil that is imparted by this beam when it gets scattered in the cavity. That's what determines the wave vector which is picked up by the long-range interaction. In practice, Kp minus Kc, this is the wave vector which is relevant for this interaction. That's a small wave vector that happens to be smaller than Kf. So in practice, I can represent the Fermi surface, a sketch of that this way, and there would be 2 2 points here and 2 points above. These are the discrete points that are nested by the interactions. Everywhere else, since the interaction is sort of local in momentum, nothing happens, right? And now I can crank up this interaction because I can crank up laser power up to the point where this interaction becomes very strong, and then see what happens. And what happens is the following. So we do this experiment. We send the light from the side. We increase the light intensity with time in a few milliseconds, linearly like this. And what we do is we just place a single photon counter here, and we measure whether there is photons leaking out of the cavity here. That's going to indicate whether there is actually some photons scattered or not. And at the beginning, for low enough power, there's essentially no photons leaking from the cavity. Essentially, the cloud here is transparent. You shoot through it. There's very little spontaneous emission, and essentially nothing happens. And once you reach some critical pump power, then suddenly you see light that builds up inside the cavity, and you start to count a macroscopic population of photons here. Now, one thing you should appreciate here is that this is a single experimental trace, right? So this is one realization of a quantum trajectory of the system. So we really follow in real time what's going on in the system. That's something which will come handy in what I will discuss later. How does one understand this? Well, here's the point where essentially the interaction is so strong that the system wants to order. Now, what kind of order does it have? Well, it's a density wave order, which is such that it Bragg scatters this pump into the cavity. Therefore, there's actually one-to-one correspondence between seeing photons in the cavity, in a way seeing them leaking out of the cavity on the single photon counter, and having this density wave ordering inside the system. Right? And this correspondence is really at the level of operators, so this is really something which is very useful. So that's a direct signature of the phase transition. This is something which is known for a very long time. I think more than 20 years ago, the group of Vlad and Vuletic observed that on thermal atoms, and then there was landmark experiments done at ETH Zurich by Tilman Esslinger. And again, this was observed in 2021 in Shanghai on non-interacting fermions. So this is the sort of phase transition we observe as a result of this long-range interaction. One way to think about it is really like a textbook second-order phase transition. There's an order parameter, which is the electric field inside the cavity, which is 0 on average if you're in the uniform phase. And then the curvature is inverting here as we cross the threshold. And then we get a finite electric field that builds up. And that's exactly the counterpart of the density wave ordering that we are seeing in the experiment. There is a Z2 symmetry breaking, which occurs here. Simply the sign of this electric field is spontaneously broken at the transition. OK, so we can study this in a little bit more detail that we have done quite extensively. We can, for example, vary the detuning with respect to the cavity and observe that we can compensate this detuning with increasing laser power. That's where it should be if my second-order perturbation approach is actually correct. So there is a wide regime of parameters where, indeed, what we observe is basically the critical strength of the long-range interaction that's necessary to build up order. So how does one understand that? We can make a very simple description, sort of RPA, where we determine the critical long-range interaction based on the susceptibility of the system in the absence of interaction. And that's determined basically by the density susceptibility at the relevant wave vector and at zero frequency. That's an object which still is complicated because it's a unitary Fermi gas, so it's not necessarily an easy thing to compute. But that's essentially the picture which comes with my understanding in terms of free energy landscape. And if you follow this approach, you can actually predict that the susceptibility should increase and diverge at the transition. So basically, if you send a small probe onto the system and try to produce such a density wave from the outside, the system will respond in a way that diverges at the transition. This is really a measurement of the curvature of the free energy landscape that is basically shooting up at the transition. It's also where, when we measure the susceptibility, we can actually see the system harden. If we go to negative interactions, that means the susceptibility is actually decreased compared with that of the unitary Fermi gas by the long-range interaction. Of course, if we make repulsive interactions, sort of, this is actually going down forever. There's no phase transition that we encounter. So that gives us, first it gives us confidence that we have a good understanding with this very simple picture. And then now we can build upon that and ask questions, for example, about the dynamics. This is the thing which we've been doing now over the last couple of years. As I mentioned at the beginning, because this interaction is controlled by laser power, we can change it in time pretty much at will. And now what we've done is we've done quench experiments. So you can basically start at t equals 0, turn on abruptly a certain long-range interaction strength that's enough to turn the free energy landscape into that. And then you can follow through the cavity leakage in real time how the system orders. And these are individual time traces, just examples of how the system evolves after the quench. And we see gradually the order building up until you reach somehow a steady state situation. And that corresponds in this picture to your system running down the potential hill. If you go deeper in the organized phase, so if you quench to larger and larger value of the long-range interaction strength, we see this happening faster and faster. But again, we can record this on individual traces. So we can look at such traces now in a little bit more details, take many of them in the same conditions and start to average. And there, one thing to be careful is that we actually see a lot of fluctuation from one realization to the next in the number of photons that we actually detect in real time. So if you were to just compare, for example, at this point in time and average out all that, you would be averaging situation where there is essentially no photons with situation where the system is essentially fully ordered already. But we have access to individual trajectories, so we can really analyze each of them separately and recast them on top of each other before averaging. And when we do that, we find this kind of traces, which is basically now in log scale, direct signature of exponential growth. And that's an exponential growth which starts all the way down to the lowest number of photons that we can actually detect. And that goes essentially uninterrupted until we reach the steady state over about 3 orders of magnitude. Right? And this is something which is, I think, quite striking, that we see this ordering, which is essentially the counterpart of the system running down this inverted harmonic oscillator, but it does it in a completely uninterrupted way. So it doesn't encounter anything on the way that actually changes the character of the dynamics. This is something we think actually comes from the long-range character of the interaction. Okay, that also means that this dynamics is actually very simple because it's described by one time scale or one rate. Right? So we fit now these rates as a function of the different parameters. We vary now how deep we go into the ordered phase. So this is d over d0 critical. This is the critical point here, and we go all the way up to 20 or 30 times the critical pump power. We see now the growth rate, alpha, evolving from something very small here. That's basically, if you want, critical slowing down. Right? There's a time scale, which is actually diverging close to the phase transition. And what we see is that as we increase the long-range interaction strengths, we quench deeper and deeper. We see this time scale just go down, so the rate is going up, and it's going up smoothly over more than 2 orders of magnitudes. And actually, that's something which is also very surprising. These are data for the unitary Fermi gas, but when you see, this is actually the Fermi time, if you want, right? And what this means is that the system can order an order of magnitude faster than the Fermi time, and it actually doesn't seem to saturate. Right? We stop here because that's the laser power which is available to us, but it doesn't seem like we are encountering any actual limit, even way above the Fermi time, and that's also something which we think is a signature of the long-range character of the interaction. Right? This is very different from what you would expect if you had contact interaction instead. So that was for the unitary Fermi gas. We can try to understand this. So this is something that work that has been done by Eugene Demler and his students in doing simple early time dynamics and trying to track how fast the order is supposed to grow. And you can get an equation which connects the strength of long-range interaction with the growth rate. And what connects the two is, again, the density response function. And because it's the early time dynamics, you can evaluate this function on the system before the self-organization. So it's basically a property of the unitary Fermi gas. Right? And now you can take the literature, try to get the best estimate for how this function is supposed to look like for the unitary gas. And when you do that, and properly accounting for trap averaging and so on, this is the kind of theoretical prediction that one can get. I think the agreement is quite remarkable. It goes all the way over the 2.5 orders of magnitude that we actually span. And that's actually suggesting that this inverted harmonic oscillator dynamics is pretty much everything that there is to understand. There is some subtle point here for the largest rates. And this is something where we think there are contributions from modes which do not participate at the phase transitions. These are modes of higher energy. I can comment on that if you have questions. This is still a point where which we at the moment have to understand a bit better. But there we have a nice agreement. So it means essentially the picture is again very simple. Now what we can do is we can see whether this picture here is robust when we start to change the microscopic parameters. So remember, we have a gas at unitarity, but we can change magnetic field and explore different short-range interactions in the BEC-BCS crossover. And when we do that, we collect data in the very, very same way. And what's even more striking is that the data are actually exactly the same. So there's nothing you can do with short-range interaction that will change the way the system orders. And that's valid from the longest time scales to the shortest time scale all the way through the Fermi energy. This is quite striking. It even actually agrees for a fully polarized Fermi gas, where there's actually no contact interaction. The data seem to overlap very nicely. We are trying to understand this better. There are indications, at least from the theory analysis of the Demlock group. One thing which we know is that for the largest possible alpha, we have reasons to think that it actually there should be universal and completely independent of the details. That's because the function chi is constrained by some rules. There's the F-sum rule, which essentially constrains entirely the behavior at the largest rates. Now, the reason why it actually agrees all the way down here, at the moment, we think it's simply because if there would be small differences here, you see we are looking at them in log scale, we should actually have small differences. At least that's from what theory would predict. It seems trap averaging is already washing out the differences between BCS and BEC quite a lot. That's actually a partial explanation for why it seems to be so universal.
Is the modulation has a certain K vector?
Yes.
Is this wave vector larger or smaller than the Fermi vector?
There are actually, yeah.
So I would imagine if the modulation happens at shorter period at higher K vector than let's say the Fermi C, you eventually have a non-interacting model because you would expect that excitation in the Fermi gas at large K are just essentially
free particles. Yes. So that's a very good question. So K minus, the small wave vector, is actually smaller than Kf. Right? Is smaller than Kf. So this is actually relatively long wavelength modulation. There are actually two components, if you remember my schematic. So you send light from the side, and the light, it has a small angle with respect to the cavity. So there's a small wave vector and a long wave vector. The long wave vector is responsible for the dynamics at the fastest rates. This is why we think there it's actually universal, and we know that it should be, exactly for the argument you mentioned. Now, why is it also true for the sort of long wavelength part? That is not completely clear. And there we should expect differences. In some sense, the compressibility, if you take the long wavelength limit, the compressibility is actually different from BEC to BCS by a factor of 2, which is washed out again by trap averaging. That's our current understanding. So this is where we are at that stage, but there seems to be a very simple picture emerging of this system. And remember, this is a strongly correlated Fermi gas that we quench very far away from thermal equilibrium. We follow the real-time dynamics, yet this system seems to be surprisingly simple. Actually, we can go a bit deeper into that and start to try to understand basically how one can interpolate between the quench that I was mentioning and an adiabatic ramp, which would arguably try to follow the ground state. And we can do that by changing the speed at which we are crossing through the transition. And when we do that, we go from slow to fastest ramp. We can track again on these real-time traces when we actually see order kicking up, and we can track this point as a function of speed. If we go very fast, we see these points shifted up. That simply means ordering happens later. But because there is a linear relationship between time and long-range interaction strengths, that actually means that the threshold is actually pushed up. Now we can, again, vary the speed and track this difference here as the speed is increased. This is, again, something we have done over about 4 orders of magnitude in speed. And this is the relative shift normalized by the critical long-range interaction strengths that we have observed. All the colors here are for the different interaction strengths. I put them all on top of each other because essentially there's no difference also within our signal-to-noise ratio. And we see a smooth increase here that again seems to be completely universal. It actually looks like a power law. So we can go there and fit a power law exponent for each of the different interaction strengths. They all end up being pretty much the same within our error bars. It actually seems to fit also with what people had observed for the Dicke phase transition in the Hamburg group in 2015. So it seems that this dynamics, also the response to finite speed ramps, is something that is completely universal and independent of the microscopic details. Of course, this analysis simply suggests that, okay, there's some kind of critical behavior that we can extract from this finite ramp dynamics, but we can actually do better. In a sense, once we know the step response from the quench dynamics, we know it's ruled by only one number, which is the time scale. We can actually try to guess what the response to anything else might be, right? In the end, what we can write is just a differential equation that would give us the number of photons, the photon flux, as a function of the long-range interaction strength. That alpha of d we know because we've measured it on the quenches. So if we now have this varying in time, we can just integrate this differential equation and have a prediction for how the number of photons should scale with speed. And when we do that, we obtain the dashed line that is here. This is just the integral of the data that I showed you before for the steps. And what this means is basically, now, once we know the only thing that there is to know, which is the ramp rate, we can predict the response to pretty much any kind of dynamics as well. So that is, again, I think a signature of the fact that this system, in spite of being strongly interacting, is actually very simple. And that's the picture I'd like you to take home about this part. We have this long-range interacting system that has different features. The main feature it has is it has essentially one time scale, which is that of an exponential growth of order when you quench it across the phase transition. That's the only thing that actually happens all the way from the early time dynamics up to the steady state. This time scale or this rate is a smooth dependence on the long-range interaction strength. That growth with long-range interaction strength is smooth, and it can exceed the Fermi energy by orders of magnitude, as far as we can say. And it's broadly independent of any other microscopic detail, in particular the strengths of short-range interactions, bosons, fermions, and so on. And once you know that, you can actually predict the dynamics for pretty much any ramp you can find. So this is a striking picture. For some of these effects, we actually have at least a theoretical idea where it comes from, but that's, I think, the general picture how it emerges from the experiment. And we think that most of these features, they come from long-range interactions. For example, the fact that we don't have anything else at the exponential order is because the system essentially is single mode. So it will grow order everywhere at the same, exactly in the same phase. You cannot have defects that are generated through the dynamics like we would have with vortices or dislocations, because this is completely determined by the mode structure of the cavity. And same thing for the universal growth that can exceed EF. This is again because we have long-range interactions. So how am I with time? Because I see the... Okay. So now I just want to use the few minutes I have to first advertise the few things that we are doing in parallel. So if you had the chance to see the poster of Tabea yesterday, I think it's still hanging around, you would know about these things. The first thing I want to briefly advertise is the fact that we can operate the very same system, but now not only having interactions between atoms that are mediated by light, but having interaction between atoms and pairs of atoms. This is like a three-body process. And we do that because there are photoassociation transitions in lithium, such that you can have light that is Rayleigh scattered, not by one atom, but by a pair of atoms. And now the very same procedure I described will give you an interaction between pairs and atoms, and even in principle between pairs. That would be a four-body term that shows up. That's something which we have started to investigate. We have actually a few significant set of data which we are trying to understand as, again, the students of Eugene are thinking about how one should interpret these kind of things. But the main thing we see is that the critical strength of the long-range interaction that's necessary to yield organization is varying in an interesting and non-trivial way when we change the detuning with respect to the photo association transition. So when we change the admixture of these processes compared to the atom-atom term. That's something we'd like to understand. And it's really unexpected that this kind of thing seems to show up in our system. The last thing I want to show is I want to talk a little bit about imaging, because that's the latest improvement we've made on the experiment. That's the thing which Tabea has been working very hard on. And basically, so this is a simplified view of our experimental system. We have here the cavity at the center of the chamber. We have all the coils around and so on. And there is a little bit of space here which you can use in order to fit high numerical aperture lens. It was kind of a heroic alignment. But we actually now have a lens with a numerical aperture of 0.4 that we can use to now observe in situ the cloud and drive the system at the same time. So we really have now these two ways to access the physics. One is still the cavity photon that leak out in real time, and the other one is the absorption imaging. And now we do the same thing. We do ramps of the long-range interaction strengths. We interrupt this ramp at different points and take pictures like that. So this is an in situ absorption picture of the cloud, I think at 200 microseconds here throughout this ramp. And as we increase the power here at, say, 400 microseconds, this is how the picture looks like. And there you really see, I think, stripes that are showing up, and this is really like the manifestation of the self-ordering as I was telling you about before. So now it's really exciting times because we can start to accumulate these pictures and have now information that is both the photons and the atoms simultaneously and independently. If you zoom here, you really see the stripe pattern having the right orientation as determined from the geometry of the pump laser and the cavity direction. So these are single-shot images on which one can actually see these density waves. And now, of course, one can try to understand. So this is work in progress, trying to understand the contrast of these, how it evolves with the different parameters, and how we can convert this contrast into actual densities, which is not completely straightforward. But that's the thing which is going on. And once we know that, we can look at things, for example, like correlations between photons and atomic patterns over single shots. And remember, we even have access to the whole quantum trajectory of the system. So we have time traces of the photons, which we can now hope to correlate with how the picture actually looks like. There's a very rich amount of information that we are working on at the moment. So with that, I will just leave you with this summary. We have this tunable Fermi gas that has long-range interaction and short-range interaction at the same time that shows the self-organization physics. We see this universal dynamics that's kind of unexpected, at least for me, that a system which is that complicated ends up being described by such a low number of parameters. And then we now have this new in situ imaging capability that we will leverage for future experiments. Thanks for your attention.
Questions? So Philippe, is there a qualitative difference with bosons, or is it more the details? I mean, you talked about that there's universality interactions.
Can you use your seat mic, please?
That interactions matter only very weakly, but what about the quantum statistics?
We cannot go very far on the BEC side. So as far as we have explored, we compared BEC side of the Fishback resonance with fully polarized fermions. There seems to be very weak differences.
But theoretically, if you would look just as rubidium or lithium-7 in terms of theory.
Let's say on the fastest for the fastest growth rate, so the asymptote, that one should be universal, that we know from first principles, sort of. Now, all the way down to the critical point, it's unexpected. We don't know if it's an accident of our experiment. I've asked repeatedly to the Slinger group and the Hamburg group if they had done such experiments, which are relatively simple, and if they could show us how it looks like. It doesn't seem that they were actually interested, or at least they couldn't find back in the past, but I would be really curious if an actual rubidium experiment could do that, and it's probably not a complicated experiment. So it just, would be extremely exciting if it's actually still quantitatively the same.
Jean-Philippe, you had normalized in the rise time of each trajectory such that you get rid of these shot-to-shot fluctuations of the onset. Can you say something where they come from, these shot-to-shot fluctuations? Is this
yes, that's it's a very good question. Thanks. So there are. Okay, in this unstable dynamics, right, you start essentially from some initial fluctuations, which is sort of growing in time. So the current interpretation, and that's based on our discussions with Eugene and his students, is that it's initial thermal and quantum fluctuations in the cloud that is actually initiating the dynamics. So we think, right now we've only been fitting the growth rate, but there is the prefactor. In principle, we can try to fit this prefactor, and that, again, there should be a theoretical prediction for that, because these are fluctuations that are in the unitary Fermi gas. We're in the process of comparing with theory. On the experiment, it's actually hard. It's like tracing the zero patient in an epidemic, right? You really have to go all the way down, and then, of course, you have no signal at the beginning. So let's say, as far as we can say, this is compatible with that. There's also another source of noise, which is the quantum noise going in the cavity from the photonic side. That's sort of open quantum system thing that might also participate in seeding the dynamics. We don't yet know which one plays the largest role at that stage.
Okay, but temperature, for example, you can test. So this would be...
The temperature we can compare, yes.
Okay, cool.
Beautiful results and data. I want to try and understand whether the Fermi energy is a natural scale for the rates that you're talking about. I think of the Fermi time is something like the scale of collisions that you might expect for a non-polyblocked, let's say, Fermi gas. Okay, and so does the process you're thinking about require a collision, or is it an atom-photon? I'm trying to understand what the atom-atom role is in the rate that you're showing us.
Yeah, so my understanding of that is that, as you say, for contact interaction, the Fermi energy is the natural scale because it's of the scale associated with interparticle spacing. Here, with long-range interaction, so it would be a light-assisted sort of interaction, and that is not constrained by the Pauli principle because it's completely non-local. So in that sense, I would say you need sort of a collision if you want, but that's a long-range interaction type of collision, right? And that, of course, will scale up as we increase this interaction strength, and there's no limit how high we can go. That would be sort of the very simplest explanation I could give.
And so why did you then choose EF as the scale, to make it non-dimensional? Would there be an atom-photon or atom-photon-atom parameter that is a more natural scale?
We could use the dispersive shift, for example. That's sort of the collective coupling, dispersive coupling to the cavity, but that would be the same all the time. So that wouldn't change much. It would just rescale the overall axis number. But I think when you want to compare BEC, BCS, and unitary gases, it seems Fermi energy is kind of a relevant time scale. At least that's the natural one we could find. Also because we think the growth is determined by this response function, and the response function has natural units, which is the Fermi energy as well. So that's the natural normalization that will anyway come out when you try to compare with theory.
Thank you.
Temperature plays in the gas, and if you can change it. And
let's say it's not easy to change temperature by a lot without changing a lot of other things. So as far as we could say, it doesn't seem to play a big role within the range where it has varied, from one day to the next and this kind of things. This is something we'd like to study if we manage, for example, to make a box in the future where the density would be fixed and you could really vary in temperature, everything else equal. I would say within our current understanding, you're going to change slightly the response function, the value, but the overall behavior, in particular, once you rescale by the critical strength, that should be very weakly sensitive. That would be my gut feeling.
Okay, probably the last question to be on time.
I think I have a maybe more basic question. For the cavity, how do you end up with a Gaussian trap and not pancakes?
Very good question, thanks. There's a trick, and the trick is the following. If you're at the center of the cavity, and the mode number n and the mode number n plus 1 in your Fabry-Perot cavity, they are shifted exactly by pi over 2 at the center. Right? So one is a sine, the other one is a cosine. So if you drive the two simultaneously with the same strength, the actual potential is cosine square plus sine square. So actually, you just put an electro-optic modulator on the path of your cavity. You modulate exactly at one free spectral range. And there's a magic power of the modulation where the entire lattice goes away. And Tabé has seen, undamped dipole oscillation in the unitary Fermi gas along the cavity in this kind of trap. That's really nice. No alignment, nothing. Just a 2,500 euros modulator.
Okay, let's thank the speaker.